Today, we will be going through various types of different truth tables. The tables that we will be going through are the AND truth table, OR truth table, NAND, NOR, and XOR truth tables. If you've ever wondered how a computer actually decides what's true or false, this is where it basically starts. A truth table is a simple way to list every possible input to a logic system, and it'll show exactly what an output is, what output you will get. To help visualize this concept better, I will be using an open and closed circuit examples to help visualize each table to get through each example. We're going to start off with the AND table. So I wrote out the AND truth table already, and as you can see, the inputs in blue are A and B, while the output in green is actually just Y. So to actually help you visualize how this looks, I'll draw a circuit where a very simple circuit with two switches where we have power connected to, let's say, an open switch, which is connected to another open switch, and that's connected to the output Y. So what this basically means is that this open switch actually represents the input A, and this second open switch represents the input B. So now let's say we are looking at this row over here where it says input A is 0, input B is 0, and output Y is also 0. So for Y to be equal to 1, the current going from power over here actually has to reach all the way to Y without any interruptions. So meaning both A and B need to be closed, which in this case, they're actually both open. So now if we look down over here, we can see that we know that if an input equals 1, that means it'll be on. And if the input equals 0, that means it'll be off. So right now, we know A and B are both 0. And for it to be 0, we know 0 equals off. And if it's off, that means we're going to put an open switch, which is exactly what we have for A and B. This is why the output Y is equal to 0. Now let's look at the next row, because the next row is actually going to show that this time A is equal to 0, so A is still an open switch, but this time B is actually equal to 1. So if B is equal to 1, we know it's going to be on. And if it's on, that means it has to be a closed switch. So we're going to adjust the circuit by erasing B and replacing that closed or open switch with a closed switch. So now current's actually going through. But notice how the output Y is still equal to 0. And this is because of how A is preventing the current from going all the way through Y. And because of that, the Y will still be 0. The third row actually is very similar to the one we just did, where instead of B being closed, A is actually closed. I'm not going to redraw the circuit for that because all you got to do is flip the open it's closed currently. But notice the last row now. We'll deal with the last row, which is they're all equal to 1. This is when A and B are both going to be closed switches. And as they're both closed switches, this means that current's finally able to go from the power area all the way to Y, meaning Y will finally be equal to 1. So now let's look at the OR truth table and explain how it works in the circuit manner like we did for the AND truth table. So let's say we have another power, but instead of this being a series circuit, we'll actually make it a parallel circuit with still an open switch, all connecting through, and then it'll reach an output Y. The difference between the series we had earlier and the parallel now is that only one of the paths need to work for the power to reach Y, whether it's going from the bottom path or the top path. As long as one of the switches closed, meaning one of the inputs is equal to 1, because we know 1 is equal to on and on equals close switch, that will lead Y to be also equal to 1. This is proven on the truth table, but I'll actually visually show it now. So let's say we're looking at the first row actually. We're looking at the first row, 0, 0, 0. AB is equal to 0 and Y is also 0. That means, also let me label these uh, or yeah, let's label these closed switches with the colors. This will represent A, and this will represent B. So we're saying that both switches A and B are open, which in this case there are, and because they're both open, the power is unable to reach Y, so Y will be equal to 0. That's the first case. The second row actually shows A equals 0 and B equals 1. So A equals 0 means 0 will be off, and off equals open switch. So 0 will, or A will remain open, and B will actually close. We'll actually close the B switch. And notice how when we close the B switch, I got rid of that accidentally. Notice when we close it, we now have a path, a bottom path connecting straight to Y. And because we have a bottom path connecting straight to Y, Y will equal 1 as well. So that's kind of nice. Similar for the third row, instead of B being closed, A will be closed. So to change this, we have to open up the B switch because it's equal to 0, and we're going to close the A switch. And there, instead of having a bottom path to Y, notice how the top path connects to Y perfectly. And because the top one works, Y is again equal to 1. Now, looking at the very last row where both of them are equal to 1, A and B are equal to 1, that means both switches are closed. And because both these switches are closed, it has two paths available to each reach Y. As long as this is one path, this will always work. So A and B equaling 1 will result in the output Y also equaling 1. Now we will be going over the NAND truth table. A NAND operation is basically an AND operation with its output inverted. This is why the circuit that I've already drawn is very similar to the one that was drawn for the AND truth table. The only difference being this operation. So let's say we have an AND and we combine it with something called a NOT, which the NOT can be shown through this inverter. What this basically means that every output you got for the AND can be inverted. For example, for a normal AND table, this would be 0, this would be 0, 0, and 1. But because this is called an AND, we actually change this. We invert every single answer we just got to get 1, 1, 1, 0. So instead of memorizing like that, we could visually show this by using the new NOT or the inverter, integrate the inverter into the circuit that we have. So let's follow the same logic we've been applying throughout the other examples where A is equal to 0, B is equal to 0, and Y is equal to 1. This means that because I said earlier no current is able to go through here, the actual operation right here, or the actual binary value will be 0. But if the 0 goes through a NOT or an inverter, this 0 will actually turn into a 1 over here. And because it's a 1 over here, the output for Y will be a 1. A 1. So using that logic, we keep going row by row and getting as much as possible. So looking at the last row, we'll see that A and B are both equal to 1, and the output Y will be 0. So let's quickly show why that happens. As A is equal to 1 and B equal to 1, we know that means it's going to be a closed switch. So A will be a closed switch, and B will be a closed switch. So because they're both closed switches, we know that the current is actually going all the way here up until this point. And up until this point right here is equal to 1. The binary value will equal to 1, meaning it is on. So as that binary value 1 goes through the inverter, it'll then go the next point after the inverter, it'll actually equal 0. And that's what the Y value output is actually reading, which is why the output for Y is 0 when A and B are equal to 1. So now let's look at the NOR table. The NOR table circuit looks very similar to the OR table circuit, and that makes sense because of how the NAND table looked very similar to the AND. The only difference being, again, is this inverter we'll call the not because this inverts any value here to its complement over here. So again, looking at the first row, we could see that when a equals 0, b equals 0, the output y will be 1. This is because, again, as we go through the power, and we know that if it's open, if a and b are both open, the value here will be 0. So by the time it gets through the inverter, the value here will be 1. So the value y is equal to 1. The last truth table that we will look at is the XOR table. XOR stands for exclusive OR. It'll only output 1 only when exactly one input is 1. If both the inputs are the same, then the output will be 0. So let's say for this example, we have a equals 0, or let's look at the first row actually. We have a equals 0, b equals 0, and y equals 0. Notice how a and b both equal 0. So then because of that, the y has to equal 0 for this case over here. Now, looking at the second row, we'll see that a equals 0 and b equals 1. Notice how they're different inputs. A and b are not the same. And because of that, y will equal 1. Looking at the third row, same thing, but this time a is equal to 1 and b is equal to 0. And as there are different inputs again, y will equal 1. And now we look at the final row where a is equal to 1, b is equal to 1. And notice how they're the same. Because they're the same inputs, or same value at least, y will equal 0. That basically wraps up the video on truth tables. If you guys have any questions, please let us know. We'll be more than happy to help you guys. And yeah, thank you for watching.